A less common situation that we might face, but nonetheless one that might come up, is where we end up with a characteristic polynomial that has repeated roots. Now remember, the characteristic polynomial is just the quadratic equation that we end up with set equal to 0 that we need to find the roots of. For example, we know that a parabola can cross the horizontal axis at either 2 points, which we've called these perhaps R1 and R2. Not necessarily the case that one needs to be negative and one needs to be positive. This is just to show you the idea. We could have two distinct roots. We could have just one distinct root repeated, right? We say repeated because in the quadratic form, negative b plus or minus, right? And in the event that what we get under here is the square root of 0 over 2a, well, in that case, we'll just get negative b over 2a plus 0 and negative b over 2a minus 0. And for all intents and purposes, that's just the same root repeated twice. And that normally would appear like this, where we see the parabola just touch the horizontal axis. And then we've already seen the complex roots case where we don't actually have, where we have what we call two complex roots. Okay, so like here's an example of one, and this one's actually factorable, x plus 4 quantity squared, right? And then at this point, this would be set equal to 0, and we basically just get x equals negative 4, and we get it twice, right? So we'd say x is negative 4, x2 is also negative 4. We might think this is fine. We plug it into our general form. We say, well, okay, e to the negative 4t and e to the negative 4t. So we have k1 e to the negative 4t plus k2 e to the negative 4t. And there doesn't seem to be anything wrong with that, except that notice there's a common factor of e to the negative 4t in both of the terms, and therefore you could factor that out and you're left with the coefficient k1 plus k2 all in front of e to the negative 4t. And that may not seem like a problem at first either. But let's say you have two initial conditions now, one for position and one for velocity, or rather the function's initial condition and its derivative's initial condition. So in this case, we would plug in 1 for y, e to the 0, we just get k1 plus k2. You take the derivative of this guy, and y prime would be negative 4 k1 e to the negative 4t plus negative 4 k2 e to the negative 4t. And so you again plug in 0 for t, and that just becomes a 1. And so we get negative 4k1 minus 4k2. But here's the thing. If you divide both sides by negative 4, right, you get 1/4 on the left, and then you just get k1 plus k2 on the right. But statements. One of them says, the first one says, k1 and k2 need to add up to 1. But the second one says k1 and k2 need to add up to 1/4. And we know that you can't add the same two numbers and end up with two different results. And so that's a contradiction, and therefore we could not satisfy a position and velocity initial condition at the same time. So this method fails in that regard. Is it a solution? Sure, but it's not a useful one because we can't control initial conditions for the function and its derivative. So we'll propose the repeated roots theorem. And this one might look familiar. This actually occurs also whenever we have first derivatives where they look something like this. Something like negative 4y plus, I don't know, 5e to the negative 4t, where the coefficient here and the coefficient here are the same. We actually saw this type of solution. Well, all we're going to do is when we get two identical roots, r1 and r2, and we'll just, since they're going to be the same, we'll just call them both r to keep it simple. Then the solution will just be slightly modified. Instead of both being e to the negative 4t's, well, they won't both be there, but we're going to preface it with this coefficient of t in front of the second term. Or, I mean, you could call this k1 t e to the rt and call this k2 e to the rt. Makes no difference. So in our case, that would be y equals k1 e to the negative 4t plus k2 times t e to the negative 4t. And now when you take this guy's derivative, you still get negative 4k1 e to the negative 4t But here you have to use the product rule because you have a function of t times another function of t. So the derivative of the first would be k2 times the second unchanged, plus the derivative of the first, which would be negative 4, derivative of the second, which would be negative 4 e to the negative 4t, times k2t. And now you notice that these two terms right here could actually be combined into one. This will be negative 4k1 plus k2, all times e to the negative 4t. But in the second one, you get negative 4t k2 e to the negative 4t. And now when you plug in 0 for t, don't let this intimidate you, this entire term will become 0, right? Because we have negative 4 times 0 times something is going to be 0. And then when you plug in 0 here, you get a 1. And so now you get y prime equals negative 4k1 plus k2, which does not pose the same problem because there's only one factor of negative 4 instead of two factors of negative 4. So that in a way seems to resolve our problem, where now you could plug in negative 1 for y prime, and your second equation looks different. Your first equation evaluated at 0 will actually just give you the value of k1, because this term right here will be 0, because you plug in 0 for t. And therefore, you'll just get 1 equals k1. And then you get k1 is 1, so you could plug that in here. And then k2 will actually end up being 3. And therefore, that works out, and we're able to satisfy both initial conditions. Now, if you're curious why, here's why. Why does this work? Well, we won't derive where it comes from. Rather, we'll just show that it works. Okay, so here's what's happened, right? We had a situation where we get a repeated root. And so a repeated root will always allow you to factor your quadratic into x plus r quantity squared, right? You'll get that same root twice. And you'll set that equal to 0, of course, right? Because you're looking for the value of r that will make that equation true. But if you actually expand this out, you'll get x squared plus, you'll get an rx plus another rx, will give you 2rx. Remember, you can't just square both terms. And then plus an r squared. Okay? You'd have to maybe write it like this to see this. And when you do this, you're going to get this equation here, right? And what we want to illustrate is that in situations where this guy is twice the value of r, and this is the r squared. So notice that if r was equal to 1, for example, what we would have is x squared plus 2x plus 1. Okay, that's a perfect square. If r was 2, then you would get x squared plus 2 times 2 plus 2 squared. And we've seen these ones before. These are perfect squares again. So how do we know that this will work in situations where your equation looks like, or your quadratic polynomial looks like this? Well, this polynomial actually comes from when we have our second derivative plus our some multiple of our first derivative plus some multiple of our function equals 0, right? This is a homogeneous second order equation. Now, the 2r actually would come from the fact that we would have a coefficient of 2 right there, and a coefficient here of r squared. And you're like, okay, well, how do I know that from just looking at the equation that this is true? Well, remember, our guess is of the form e to the rt. The first derivative is r e to the rt, and the second derivative is r squared e to the rt. If we plug everything in, we'll get r squared e to the rt plus 2 times r e to the rt. And here we'll get plus r squared e to the rt